Okay, folks, it's time to look at another Diels-Alder reaction. So let me give you the general template setup because I want to focus on just product formation, and then I'm going to include another older topic that we have discussed. All right, so let's say that we have a diene, a conjugated diene. So I've set it up the right way, right orientation. And I'm going to add to this maybe a carbon double bond carbon. And off of this top carbon, let's put a C with a double bond O and an OCH3. All right, that's something new. We haven't really seen that too much, right? It's an ester group, by the way. That's what that's called. And then down here at the bottom, let's put a CH3, a methyl group. If these two things react, what forms? So I need you to get comfortable doing the major product. So keep the conjugated diene in the same template. There we go. There's the start of it. This double bond moves down, goes here. This double bond goes out to grab onto that new carbon that we have here. And then that double bond moves up to grab on to that top carbon of the ring. All right, so there's the ring formation. So what I'm going to do, I'm going to leave these carbons in boxes, and I'm going to draw them as C's so you have a point of reference. All right. Otherwise, we would have done a skeletal structure. We would have cleaned that up a little bit. We would have just really done a cyclohexene ring and called it a day. Well, off of these groups, off of these carbons, we have two groups, and those groups don't change. They're still there. So we have a bond that goes to a carbon, double bond O, with an OCH3, and then we have a bond that goes down here, and that goes to a CH3 group. Not a big deal, right? But there's something I want you to pay attention to. And that's stereochemistry. Look at what I've done. I've now incorporated another lecture module that we have recently talked about, stereochemistry, into this world of conjugated dienes, dienophiles, Diels-Alder's reaction, delocalization, looking at the reactions of alkenes and naming maybe alkenes. All of it gets mushy. I've told you and I warned you over and over. We can talk about stereochemistry here. How? Folks, look at this double bond. That's an alkene, right? That double bond is an alkene. And that alkene has a double bond, and that double bond does not allow rotation. Pretty important. What does that mean to me? Well, that means there's geometry around this double bond. And if I asked you back in the day when stereochemistry and double bonds were introduced, and I would say, hey folks, let's name this, but keep stereochemistry in play. Well, you have to understand that carbon has a fourth bond. That fourth bond, folks, is a hydrogen, and this fourth bond is a hydrogen. So looking at this alkene, is that cis or trans? Oh. That's what he means by stereochemistry. Yeah, that's right. The hydrogens are on the same side of the molecule, right? We see this curve. We see this kink. The high priority groups are on the same side. Folks, because of that, this is a cis. And stereochemistry is kept intact when a Diels-Alder reaction goes forward. And this is something that we really haven't discussed. We could have been talking about stereochemistry this entire time with reactions, but we didn't. And here's our first encounter with this, because now we know what stereochemistry means. So when these two molecules come together, when they form the ring in the Diels-Alder reaction, it keeps the stereochemistry. So if we have to be particular, sometimes we don't. Sometimes we just don't care. We just draw the product and we go on to the next problem. But sometimes they want those details from you. So if I look at this double bond and I see that that has a hydrogen and this has a hydrogen, they're pointed in the same directions, they're on the same side, so that means they're cis, then that means these groups will also be cis when the ring forms, because the ring is very much like a double bond. Once this entire ring has been formed, folks, it locks everything into place. There is no twisting, there is no turning. I mean, yeah, we can talk about equatorial and axial bonds and that type of thing, but once they go on, they're either pointed in the same direction or they're pointed in opposite directions. We could care less about axial and equatorial bonds. That just gave us an idea of stability. That gave us the idea if things were on the same side or opposite sides. But here we know for sure. The starting alkene was a cis. Therefore, in this product, on that side of that molecule, they need to be cis as well. So what that means to me is that I have to show that, and I have to do a wedged bond, and I need to do them both shaded. Or you could also do them both dashed. Doesn't matter. As long as they are on the same side. And that represents that. The two shaded wedges represent same direction. They're both pointed toward me. If both of these were dashed wedges, that's great too, because that means they're both on the same side. They're just pointed away from me instead of forward. Either one of those would work. Doesn't matter. Doesn't matter which one you choose. You're doing a correct answer. Now, in addition, let's take a look at what would happen or what we would need to do if that wasn't the case. So here is my conjugated system, and now let's take this carbon double bond carbon, and we'll keep the same groups on here just so that you can see the difference. So I'll write the C double bond O OCH3 in the same direction that we did before, and now I'll do my CH3 group like this. I'll kink it over to the left. This no longer is a cis anymore, because that carbon has a fourth bond, that's a hydrogen. This carbon has a fourth bond, and that's a hydrogen. Just like before, the two pieces come together, folks. So I'll set this template up first. That double bond shifts to go to the center. This double bond shifts to go out and grabs a hold of that carbon. That carbon is attached still to the carbon up above, and then this double bond shifts up, and that connects the ring together. So there we go. There's the cyclohexane ring. On this carbon, we still have that C double bond O OCH3 on it. Still there. Here, though, it gets a little tricky. How do I show the CH3 pointed in the opposite direction? I mean, it's not like that one up there above. I mean, how do I do that in the ring? Look, it looks like this bond is taking that spot. So the only way that I can do that is if I do point it out in that direction and put a CH3 group on it. But to someone that doesn't know what the structure was beforehand, they're going to assume that these were on the same side of the molecule, and they clearly were not. They were on opposite sides here. This is a trans, folks, right? I see a hydrogen here and a hydrogen there, and they're on opposite sides of that double bond. So I need to be able to show trans sometimes in the products if they really want me to do this. So if the question says, predict the product and show the stereochemistry, okay, that's what they mean. Are they pointed on the same side or different sides? So up here at the top, I'm going to draw a wedge, and down here at the bottom, I'm going to draw a wedge. I know that they're on different sides. The way that this molecule is drawn, though, I need to clearly illustrate that, and it's very hard to do as is. So the way that we fix it is that we choose one of them and we put a solid wedge on. It doesn't matter which one. I don't care. Just pick one and fill it in. And then the other one has to be a dashed wedge. Again, it doesn't matter which one. Just pick one and do the dashed. That lets me know these are on opposite sides. The ester group is pointed toward me. The methyl group is pointed away from me. So stereochemistry stays intact. We can form chiral centers. If we form chiral centers, folks, we could get racemic mixtures. R and S's both could show up. We're not going to go that far into it. But these are things that we need to kind of think about actively. Because as we go further in this class, all of these things we're learning about, and it just blossoms up the organic chemistry even more so. This reaction, we have a term for this. This is called a syn, S-Y-N, all right, S-Y-N, a syn addition. That's a fancy way of saying everything stays intact. If we have a cis, we end up with cis. If we have a trans, we end up with trans. No difference at all. This is a syn addition. That's what we call that. The other way would be called anti-addition or anti-addition. So let's look at another example. Let's do a CH2 double bond, CH single bond, CH double bond, CH2. And we're going to react this sucker with CH2 double bond, CH, C triple bond N with a little bit of heat. What forms? Okay. Looking at it now, kind of hard. Very difficult. So what we decide to do is we'll rewrite this conjugated diene system, and we'll look over here and find my double bond, and it's right there. So we'll just do double bond straight up and down. And it looks like off of one of these carbons, I have a carbon with a triple bond in. All right, so I'll just kind of kink this out like that, and there we go. So I'm going to set my template up. There we go. Predict the product. All right, not a big deal. So I look at my conjugated diene. This double bond moves inward, so I'll create the setup. That double bond shifts, and it goes in the middle. This double bond shifts out, and it grabs a hold of that carbon. That carbon is still attached to the carbon up above, and then that carbon takes its double bond and shifts it and connects it to the top piece of the diene. So there is the ring formation. Off of this carbon that we see down here at the bottom, I have a C triple bond N. There's your product. That really is should all there be to answering these questions. But just because I mentioned chiral centers before, just a minute or two ago, let's look at this. This is not a chiral center. There's two hydrogens that are there. They're not drawn. They're understood to be there. This one's not a chiral center. There's a double bond. There's not four different groups. This one is not a chiral center. There's double bond, no four different groups. This one's not a chiral center because there's two hydrogens on that molecule and I need four different groups. This one is not a chiral center. It has two hydrogens. It can't be chiral. This one, though, yep, that's a chiral center. Right there. Why? It has four different groups on it. You're going to say, well, wait a minute now. It's got four different groups. This carbon is attached to a carbon with a double bond, and this carbon is attached to a carbon without a double bond. Those two carbons are regarded as different. Even though they're both C's, it's just like this C. That carbon is triple bonded to a nitrogen. All four groups are different there. There is a chiral center at work. And that chiral center can lead you to a R and an S form. And we actually get both. Because, folks, what that means is that sometimes this diene can come in just like it is, just like it's drawn, and give me one of the products. And then sometimes this whole thing can flip around. I can still line up the double bond the way that it comes into that structure, but when it flies in, this C triple bond N could actually be on the left-hand side, not the right-hand side, and that would be okay with it too. That ring is still going to form. And it's just really statistics. It's just really random. Now, there are factors at play that I can use to figure out, well, which one is going to be more preferred over the other, which is why I say statistics in a way. But for us right now, both of them are going to form. We need to acknowledge that. We need to never lose sight of chirality and chiral centers and what that means in organic. And that is a very special center because we know what that center can do. It is different. So the way that we do that is that we acknowledge this and we say, hey, sometimes this can point forward, just like that. And if I want the other version, well, sometimes this can be a dashed wedge, just like that. Which one is R and which one is S doesn't really matter. I'm never going to really ask you that with a ring structure. We just need to acknowledge that these are different. A molecule like this pointed toward me and a molecule like this pointed away from me. We now know R and S's and the importance of those chiral centers. So I can represent both of these just like that. All right? So we do get both. Never lose that sight. Let's take a look at another example. Let's say that we have a conjugated diene and something that looks like this. What? What on earth? He wants me to react this thing now? Yeah, I do. No difference. No difference than what we've been doing. Just don't lose sight of the template of the Diels-Alder reaction. So what I mean by that is start off with this conjugated diene and rewrite it just like this. That double bond moves into the center just like that. This one moves out, grabs a hold of the carbon in the double bond of the alkene. So that goes there. That carbon is attached to the carbon up above just like before. That one goes there. And then this double bond breaks up and it grabs a hold of that carbon to connect the ring. There's no difference in it, folks. ... There you go. What do we have left over? You keep it. You keep it just like we've always kept it. This one points out. This one points out. Then it goes down into this oxygen ring, and then that double bond O there, and the double bond O there. I know that looks awful. I know that looks ugly. I know that looks like a big, lumpy, nasty molecule, and it is in a way. But the Diels-Alder reaction doesn't care about the rest of that stuff. It could care less. It's only focused on the connection of the ring between the conjugated system and the alkene or alkyne. That's it. Everything else stays the same. Don't let these problems confuse you when you get to them. Let's look at another. Here we'll do a conjugated system with a methyl here and a methyl there. So there's a carbon, and of course here's a carbon, and there's a carbon. And this time, because I just talked about alkynes, let's do an alkyne. And off of this alkyne, let's do a C double bond O, O, CH3 again. And down here at the bottom, let's just do a hydrogen. There you go. I did it linear, just to represent the linearity of that triple bond instead of kinking them over. Just kind of keeping it true to the structure and geometry of the molecule. How do we do this? Same way. No difference. I start off with this template. There you go. Right? However, the difference here is that I have a methyl group that points up and a methyl group that points down. So I need to include those right there. So this double bond shifts down. It's going to go here. Oh, look at the boo-boo that I just made. I got a little bit happy with my pen. All right. So that double bond shifts down to go here. This double bond pokes out to grab onto that carbon that's triple bonded. That carbon is attached to the carbon up above. That carbon takes one of the bonds and moves them out to grab the carbon on top. There we go. But look at what I just said. It takes one of those bonds and it moves them up. What do we have left over with here? Well, this normally would have been a single bond, but we started with an alkyne, not an alkene. So what we have left over is another bond. We can't forget about that one. It's still there. We only used one set to make the connection. So that triple bond has been broken to a double. Well, off of that top carbon, folks, we still have a C double bond OOCH3. Down here at this bottom carbon, we still have a hydrogen. I can write that there if you really want to see it. Well, right there it is. If you don't want to write it, don't write it. Just leave it off. Some people like to include it because they feel like the compound is more complete. They see it here, and they say, well, why not show it there in the product? And I'm okay with that, whatever. Doesn't matter. But there is a first example of an alkyne reacting with the conjugated diene. Now, let's take it another step. Conjugated diene, and this time we are going to react it with a molecule that looks like this. What forms? Okay, use the template rule, and Tracy said that everything should be okay. Try it if you don't believe me. All right, so we'll do the conjugated template here. This moves in, goes there. This moves out, connects to that spot, so there we go. That carbon is connected to the carbon from up above, and then it takes its double bond, moves it out, and it connects the ring. There you go. Then, Tracy said, keep everything else the same. All right, so that's what we'll do. Up it goes, down it goes, and we form this other ring just like this. Good. That's your product. But it doesn't have to stop there. We can go on. What if I did 2 moles of this stuff? This reaction can go another step. Why? Folks, I've just included another conjugated system. And what I have here is another double bond. I have an alkene in here. Not only that, but I'm going to have a mixture. I mean, I have an alkene right there, and I have an alkene over to the right-hand side. We're only going to draw one of those examples. I'm going to make it symmetrical for you, just so that you can be happy with it. But now we start to see some complications of Diels-Alder. Because if there's any alkene that is left behind, that alkene can react with another mole of a conjugated diene. It's still a dienophile. It still can react with it. I mean, that's its definition, right? So what I would do is that I would redraw that molecule. Another diene will come into the picture. That gets super close. And the same thing happens just on the right-hand side instead of the left-hand side. No difference in it. This moves down. This moves out to connect. This one moves up to connect. And we get a ring that forms on that side. Just like we did in the first step, folks. So I'm going to draw this a little bit prettier for you. And we're going to have a cyclohexane ring that forms just like that. I could have done it over here to that side as well. Whatever floats your boat. But you need to keep in mind that these can be multi-steps. Let's look at another. Just to get more and more comfortable with them. CH2, double bond, CH, CH, double bond, CH, O, CH3, and then a CH2, double bond, CH, CH, double bond, O. React these two things together. All right, we can do this. Not a problem. I see a conjugated diene to the left. Double, single, double gives me trouble. And then I see an alkene to the right, so that's a dienophile. So I have a conjugated diene, and I have a dienophile. The ingredients needed for a Diels-Alder. I just need to set this up the right way. So I know that in order to do this, my conjugated diene has to take the shape. There is the carbon double bond to the carbon, right? And then that's on a single bond to a carbon, so that would be that one. And then down here at the bottom, that is a carbon double bonded. But off of that, I get this OCH3 group. So I need to include that, and it's on this carbon right there, which is okay. And then I'll take my alkene, and my alkene is straight up and down. And it looks like a CH2 was on one side, so nothing really. I don't have to draw anything. It's just two hydrogens. And on the other side, it looks like that carbon has a C double bond OH group on it. All right, so here I'll kink it out, and I'll do C double bond OH. So there's the correct template, I guess, if that's what you want to call it. And now we need to morph the two together. All right, so that's going to be pretty easy. Now that the template's there, this double bond moves in to go here. That double bond moves out to connect to that carbon. That one's connected to the one up above, and then this moves up to connect to that top. So there's our ring structure that we formed from the Diels-Alder. Well, it looks like this carbon down here at the bottom had an OCH3 group. All right, so there we go. I'll keep that there. And then it looks like this carbon next to that had the C double bond OH group. All right, so that's where that goes. Not a problem. That is correct. You just gave me one of the products for the reaction. Notice what I said? One. Why? Because what if someone came behind you and said, I'm going to set up this Diels-Alder. I need to figure out how to get this product. So I need an H on one side and a C double bond OH on the other. They could have flipped that second one on you. No one said that you couldn't do that. Remember what I said about stereochemistry and 3D arrangement? We can get different molecules out of this thing. That's not a big deal. And this question would have said, show all the products that could happen. Okay. Well, same kind of thing happens here. There's my setup. Double bond moves in, goes there. This double bond pops out, connects to that one. That carbon's connected to the one from up above, and this double bond pops out, and it connects to that one. Down here at the bottom, there's my OCH3 group. It's still there, so I don't move it. And then now that C double bond OH is up here at the top, that's going to be this carbon. So C double bond OH. Folks, these are two different molecules. This is number one, and this is number two. In this case, the OCH3 group and the C double bond OH group, this is an ether. That's an aldehyde. These two groups are side by side. In version 2, because of the way that you ordered it, ring still forms, but this time they are not side by side, are they? The ether group and the aldehyde group are separated by a carbon. So that truly is a different molecule. And we can get both out of here. And that's how this question would have been stated. It would have said, draw all the products that could form from this reaction, because they want you to understand that the way that you order these up, the way that you draw them, sometimes can be pretty important. Now, sometimes you'll put them together and you won't make a change. And we've seen that in some of our earlier examples. There's no changes to be made at all, right? And if so, that's perfectly okay. Not a big deal at all. But I do get two different versions. Here's a question I want to leave you with. What diene and dienophile has been used to prepare this product? Remember back in the day when we did synthesis problems and I said, hey, we've made this. How did we do it? That's what they're doing here. Hey, we've made this molecule. How did we do it? And they're letting you know that this was done with a Diels-Alder reaction. Because they're telling you a diene and a dienophile has been used to make the product. How do we do it? So before you hit play on the next video, can you figure this out? If this is our product, how do you rip this product apart in order to get the proper diene and the dienophile that has been used to make this product? A lot of people are okay with this when they see it the first time, but see if you can figure it out. And then once you think that you've figured it out, hit play on the next video and double check your answer. See if it's true. I'll see you then. Good luck.